Thank you. So it's really my pleasure to be here. I'm Jérémy, and I'm going to present some work I've done with Joseph and my advisor Cătălin when I was at the Max Planck Institute for Security and Privacy on mechanizing some secure compilation proofs. So first, what exactly is secure compilation? So typically, when the developer will write a program, they will write it in a source language, and they will use some high-level abstractions like types, structure control flow, sometimes even verification or static analysis to reason about the security properties of their program. But that's not actually what's going to run on the machine. So typically, the developer will use a compiler to produce some low-level code that will be executed on the machine. And in this low-level language, the high-level abstractions are not preserved anymore in general. So you might think, well, this is not really a problem. We can just use a correct compiler. And then, obviously, all the high-level abstractions are going to be preserved. Well, in fact, it's not completely true, because in practice, your low-level code is being linked with libraries, low-level code, so libraries that have already been compiled, that form a context. And this context is most of the time unverified, untrusted. It might be full of bugs. It might even be attacker controlled. And so in that setting, compiler correctness does not give you any guarantee. It's not enough. Secure compilers aim at solving this issue by preserving the high-level abstractions in the compiled program. And typically, the way you prove a compiler is secure is by explaining that there is, in the source language, some high-level context that is similar or equivalent to the low-level one, which allows you to justify and say, oh, if there was a security bug in your compile program, it's already there in the source. So slightly more formally, we can define criteria such as a robust safety preservation that way. We take a compile program, P down arrow, that we linked with a low-level context C. And if it produces a finite trace M, for instance, which can be seen as a witness of a violation of a certain safety property, then one can find there exists a source context that can be linked with the source program to produce the same trace, so the same violation of the safety property. If you take the counterpositive of this, it means that your compiler preserves all safety properties that are satisfied by your source program against any context. So this gives a very clear characterization, but more importantly, the way I phrase this criterion gives a proof technique to prove a compiler secure. And it is to give a back translation by transforming the trace, M, into a context. So in 2018, and that's prior work, Abate and his co-authors designed a proof technique for RSP so that it can be mechanized in a proof assistant. The way it works is that it starts at the target level from a compile program linked with an arbitrary context that produces a given trace. It goes back to the source with the back translation producing a new context and a new program and proving that it produces the same trace. And then it uses compiler correctness to go back down, a step called recomposition to take one piece from the first execution, the P compiled, the second piece from the second execution, the CS compiled, and prove that it produces the same trace. And here, they get that everything is compiled, so they can actually use compiler correctness again to go back to the source and obtain the result that they want, that CS linked with P in the source produces a trace M. So what's really important is that the two compiler correctness theorems that are used can be that of CompCert, for instance. So that's what they designed their proof to do, to be able to reuse an existing compiler correctness proof. So here I want to focus on one step, which is the back translation. So their back translation is actually quite simple, and it works only on a trace. So for instance, here's a little execution trace. So it starts with a call from the context to the program with one argument. Then there is another call from the program to the context this time, so the other way around with the argument 2. And then there's returns. So the way the back translation works is that they're going to write a C and a P, which use a counter that records where we are in the current in the trace. And depending on this counter, the two program parts will generate the appropriate event. So in practice, we start in C. We branch on the value of the counter. And here it's at 0, so we take this first branch. We increment the counter because we're about to execute the first event. We're doing the first call, which generates the first event of the trace. Now P has control. The same happens. We enter P. We find that counter maps is 0, so we enter this branch. We increment it. We call the next event, which is a callback to C. So we go back to C. And then we enter again this, matching on the counter, entering another branch, incrementing it again, doing the corresponding event, etc., etc. Here again for P. So that's how they define their back translation. And it's really interesting because it only depends on the trace. And when they prove this back translation correct, it's decently easy for them to do so because it actually manipulates only one finite object, a trace. The logic of the back translation is very simple. It's just emitting the events one by one. And you can, in fact, just do a proof by induction on the trace. So in the end, they have a decently small proof for this back translation, which is like less than 600 lines and including comments. So it's really small. So the issue is that RSP, that I described previously, is just about safety properties. And in security, there are a lot of security properties that are not safety, but actually more general. So they can be hypersafety, that's the case of no interference, or they can be even relational hypersafety, that's the case for observational equivalence. And so the question we had was, can we actually adapt the proof technique to obtain a much stronger criterion than RSP? And with this work, we answer by the positive. Yes, we can adapt the proof technique that way. So we take a finite collection of programs, PIs, between 0 and n, and we say if each of them, when linked with the same context, produces a finite trace, mi, then we can find a single source context that can be linked with all of the source programs to produce the same traces, mi. So this is a generalization that captures hypersafety, relational hypersafety. So now, how can we actually prove this of a secure compiler? Well, here's the proof that I described. And a simple observation is that these three steps, the two compiler correctness steps and the recomposition step, they work pointwise. So for each I independently. And we really don't need to modify them, so we can reuse them as is. On the other hand, the back translation this time needs to take into account all finite traces, the MIs, and produce a single context and several programs. So this time we need to actually adapt the back translation to generate this context and these programs. So this looks a bit like that. We will prove that there exists a source context and these programs that are P0 prime up to Pn prime, and prove that for each of them they produce the MI. And if we just implement and verify this back translation, we can prove this much stronger criterion. So how do we do it exactly? Again, the new back translation must work for a finite collection of finite traces. And it's not very obvious. And what's really important is that we don't really want to look at the code of the low-level context because this would lead to some very difficult proofs. So we really want a back translation that is just a function of the traces. So how do we do this actually? Well, we can observe that the traces have some kind of structure because they are produced by the same context and different programs. So in fact, because of the properties of the language we consider, there is some kind of determinacy that says that traces can only differ because the programs did something different, not because the context decides to do something different without any input from anything else. And so the traces, M0 to Mn, can be represented by a tree that will branch on the events from P specifically, and not on the events of the context. So, for instance, if we add a few more traces to the example from before, we can have a tree like this. So we start, the first step is a call from the context. So there can only be one, but then we can consider maybe 3 different programs. So they will do 3 different things. So this, on the second line, the 3 different calls. And then it repeats, like on the left, it's again the context that has control, so it can only do one thing, etc. So the back translation we propose is a generalization of what I described previously. So we're going to use a counter again to remember where we are, this time not in a single trace, but in the entirety of the tree, which leads to several interesting problems. So we generalize the counter to record the position in the tree, and that means that the context, additionally, compared to before, now the context will need to look at the argument it receives and the return values it receives before updating its local counter. It cannot just say, I'm going to do the next event, because it needs to know what this next event is going to be, what branch was taken in the tree. Additionally, it also needs to look at the current local counter. It cannot just increment it by 1. So in the end, by generalizing, we end up with a bunch of little gadgets like this, which look at what the current counter value is, and if it's a call, look at the calling argument, then update the counter. So here, next counter is some kind of macro that is hard-coded. And then do event is also a macro that will do the right event in the tree. So we have a collection of these things, and they are ordered linearly. So one of the difficulties of the back translation is how do we go from the tree structure to this completely linear program with a bunch of branches? So in the end, the back translation function is really not trivial. It's even worse when you think of proving it correct, because the invariants that hold in this tree are not actually trivial. For instance, the context can only do one event. We have to phrase it somehow. There are no duplicate events. We don't want to have duplicate branches with the exact same event. And all the counters in the tree are unique. Finally, there's even difficulties with handling the well-bracketedness of the calls and the returns to handle the returns, because we cannot return if there was no call before it. So we divide our back translation in several steps to solve this issue. So remember, we want to produce all these programs and a single context in the source, and we start from some kind of tree. So what we're going to do is first enrich the tree with this information. So we will go from a tree to a new kind of tree with more information recorded in the nodes, like here, the counter that I was describing previously, along with a proof that this counter that is recorded in the tree is unique. Then We will also add to the tree stack information that is needed to correctly generate the code eventually. So we need to do that because the returns are not necessarily right after a call, but you can have several calls in a row and then a series of return. And we need to have a way to describe properly what branch the context will take in that kind of setting. Finally, as I said before, we need to flatten the tree so that it's easier to translate into code. So there, we go to basically a list of nodes that describe exactly the little gadget that I showed previously. And finally, we have a last step which takes this list of nodes and for each of them generates a little gadget and puts everything together. And that's where we prove things about the source language. So what's very interesting here is that we're not manipulating anything about the source language before we reach the last step of the compilation, of the back translation, sorry. And we are not manipulating anything about the low-level language except the traces. So in a way, this is a very general proof technique, and we're really hoping that we can apply it to different settings. So here, the goal with structuring the back translation like this was really to have the passes as small as possible, so it's easy to implement them. And we actually found that even in that case, it's a bit tricky to get everything right. And it's also easy to prove each of the steps correct. So how do we actually prove such a back translation in the end? Well, as you can expect, we're going to prove, we're going to equip all the intermediate languages with a notion of small step semantics. So this small step semantics, they follow a trace, and each step reduces the tree that we're considering by emitting one event, the first event of the trace. So this looks a bit like this S arrow E S prime, where S and S prime are states, E is the event that is being generated, and both the trees and the trace that is left to execute belong in this S. So in each language, we had actually checks that will correspond to future source language conditions. So for instance, so in particular, we make sure that we only had one new check per step, which really simplifies reasoning because it means that in the actual proof we will only need to reason about one thing at a time. So for instance, returns can only occur when the stack isn't empty. And additionally, when the top stack frames, the top stack frame records the right color and callee as expected by the return event. So when we add this kind of check, the state becomes contains now a stack, and we add the following condition. If we want to execute a return from the program to the context, we need to make sure that before that, the stack add on top a stack frame that records a call from the context to the program, which we're returning to. So we had these little checks everywhere. And we prove, in the end, each pass with a concert-style forward simulation. So because all the passes are really small, all the individual proofs are not very complicated. But what's actually difficult is the very last step that I described in the diagram earlier, where we flatten the tree into a list of nodes. So this is useful because it's much closer to the final code that is going to be generated, but it comes with a lot of tricky unicity and deterministic conditions, as well as existence conditions on the nodes that are actually hard to implement. So, for instance, the existence conditions are going to say that there exist in this list of nodes all the little gadgets which starts at a certain counter and expects this given argument value and update it to the next one. But also we have unicity conditions, so we cannot have duplicates. Otherwise, we might generate code where one branch is never taken. And we have determinacy conditions because context can only do one thing at a time. So we have an actual implementation in Rock, which is slightly more complicated because it considers multiple compartments. So not just a context and a program, but actually many mutually distrustful compartments. And this adds a bit to the complexity, but not so much that the proof change a lot. So just to conclude, we started from an existing proof of secure compilation from the literature, and we wanted to update it to prove a much stronger criterion. And we did so by introducing a novel back translation technique that starts from a set of traces, observes that they form some kind of tree, divide the back translation into multiple steps that are really minimal, each doing only one thing at a time. We prove each of the steps correct, and then at the end, we get to generate a bunch of source programs, one single context that will have the conditions we want for the top level proof. And we reestablish the top level proof, but with a much stronger criterion. So one last thing that I want to say is that this approach was also useful because we could parallelize the proof process. So Joseph, my co-author, was in particular working on some of the early steps, while I was able to work on the steps at the top. And this is something that we could not really do with previous back translations. So we basically half the time it took us because we were two people working on it at the same time. So I think that's all for me, and I'm really thankful for you coming and listening to this talk. And if you have any questions, I will be happy to answer.